Here we are explaining DC to DC converter. So first we are explaining some properties of DC to DC converter using the step down operation. So this is one category of DC to DC converter, step down converter, and this step down DC to DC converter we are right now we are learning with respect to R load. So how my step down DC to DC converter works when the load is R, resistive loads. Okay, so maybe your any integrated circuits or any LED, such things will act like a resistive loads. Okay, here the main thing is there is an input is DC here, we need to consider that there is an input here, okay, we need to consider that there is a supply, DC supply of some voltage. Okay, I will say that we are using a DC supply. For an example, this may be 10 volts, this may be 10 volts or 5 volts or anything, 30 volts, whatever. Instead of using a numerical number, I will write the DC source having a value, capital letter, it is capital letter Vs. Okay, so this 10 volts or Vs is converted to some other voltage. For an example, assume that we need to deliver something like 4 volts to this, okay, to this load. So how to convert this 10 volts to 4 volts? So remember, 10 volt is there with the in the input side 10 volt is there. We need to convert that 10 volts to 4 volt, and that 4 volts should be delivered to load. This is a requirement. So how we can achieve this means using DC to DC converter. So here I have shown a switch. So this switch mainly converts this input 10 volts to output 4 volts. Okay, or else input Vs to required voltage. Okay, the switch, sometimes we close the switch, so that if you close the switch, the path will be established between these two points. So current flows in this way. At the time the load is directly connected to source through this switch. When the switch is open like this, there is no connection between the load and source, so that the load is receiving zero current, or there is no current flowing to loads from source side, or else I can say that load is completely detached from the source. So this is open circuit. Okay, here using, instead of how to implement the switch electronically, we can use a transistor, or you can use a transistor. So we should use these terminals here. This is and this is control terminal. This is we need to apply some voltages to this control terminal to turn on this transistor, so that current can flow from one end to another end only in the presence of IB, correct? No, in the current transistor IB is a control. If you apply IB, so this collector and emitter is connected. If IB is 0, this collector and emitter is not connected, so that current cannot passes from collector to emitter. Instead of transistor, I can use MOSFETs, I can use IGBT also. Okay, I can use MOSFETs. In MOSFETs, so in this terminal we connect a drain, and here source, And what is a control terminal? Control terminal for a MOSFET is a gate. To the gates we are applying a pulse like this. Okay, so you can think about a MOSFETs here. We can think about MOSFETs drain and source. So now listen here right now. Okay, assume that there may be a MOSFET or IGBT or transistor it is acting like a switch. So control terminal for a transistor is a base, or a MOSFET is a gate, or IGBT also gate. So to turn on those switches I am using gate pulses or a base currents. Okay, so right now assume that somehow we have closed the switch for duration of 1 milliseconds. We have closed the switch for a duration. Assume that my requirement to convert this 10 volts inputs. So input side we are having 10 volts. We need to deliver 5 volts to load. So this 10 volts, how can we convert to, assume that we need to convert to 4 volts, 4 volts to load. Okay, so 4 volts to load. Now, so first of all, you connect the switches. You connect the switches like this. So I will write the equivalent diagrams here, somewhere here. If you connect a switch, the same circuit equivalent diagram looks like this. Vs is there here. So Vs, the switch is closed. That's the reason input is directly connected to load. Resistor is here. Okay, so input is Vs if you consider Vs, or if you consider 10 volts, input is 10 volts, correct? So if you consider it as 10, okay, actually common word here is Vs. Okay, so what is the load voltage? If you measure the waveforms using a CRO across this V0, if you measure, if you are measuring using CRO, we are observing the instantaneous values of the voltage whatever we are getting, because the current is flowing in this way. So what is the current flowing? That its value is usually Vs by R. The current which is flowing here is constant, again Vs by R. For an example, if you are using 10 ohms 10 volts and the resistance is something like 3 ohm, then how much? Or resistance is something around 2 volts, you can say 5 amps of current will flow. Resistance is 5 ohms, if you say 2 amps of current will flow. Okay, anyhow, so when I close the switch, the circuit looks like this. At the time, if you measure the voltage between these two terminals, what is the voltage in between these two terminals? What is the voltage in between these two terminals? If you measure using a CRO or a voltmeter, what it is going to show you? It is same as my Vs. How long? Until the switch is in closed state. If you measure the voltage in between these two terminals, it is same as my Vs. So I need to write, so that's the reasons the output voltage when the switch is closed, for a timings of T1, that's the reasons we are showing that it is Vs. So the switch is closed here, that's the reason the input voltage is Vs. So assume that suddenly we have opened this switch we will open. So at the time, if you write an equivalent circuits, the switch is open here, so switch is open. So this side, this switch is open, so this is open switch. So what, here there is a resistance. Then if you measure the voltage here in between these two ends, this is a load, what is the voltage it is showing you? No current is passing here, so voltage is 0. This is what this picture is showing. The voltage is 0 when the switch is open, when the voltage is Vs when the switch is closed. In a similar way, if you think that this is an instantaneous current which is flowing here, and this is an instantaneous current which is flowing here, it is flowing in this circuit, So what happens? This current value is, when the switch is closed, what is that? Yeah, current is flowing. What is the value? Input is Vs and the resistance in this path is only R. So current is, what is the value? It is constant always. Current is Vs by R. That's the reason during on time, means when the switch is closed, the current which is flowing here is Vs by R. And when the switch is open, there is no current flowing, so current value here is 0. Okay, this is my operation. This is a technology to convert one voltage to another. Then see here, then how can I say that what is an average voltage of this? Average value of this voltage. Okay, we will calculate that. Average value, we will use a term, so VA, because this is a symbol your textbook is using, VA. Okay, we have seen several times how to take an average of this. First of all, I need to find out some periodic waveform. This is my periodic waveforms, correct? This is my periodic waveform. This same waveform will repeat again and again. So from here to here, timing is T. Okay, here to here, you timings you call as T. This is a period of this waveforms. Okay, so right now, so that's the reason I have to take average. I should take a mean. Such a reason T in the denominator T. I am taking an average for this much duration. Then as usual, integration, it starts from 0, and this value, you can say here to here timings are noted as T1. Timings here to here is T1. So 0 to T1. And here to here, what is an amplitude? Amplitude is Vs. So that's all. 1 by T. Vs is a constant. I can take outside. So integration of dt. This is T. Okay. So dt is there. So Vs. So integration of 0 to T1 dt. So that is equal to Vs by R. What is integration of dt? Is T. So T 0 to T1. So this is Vs by R T1. Okay, see here. Okay, this I shown here. What is T1 means? For an example, this is my T. Okay, for an example, assume that T is 1 millisecond. For an example, you assume that T is 1 millisecond. 1 milliseconds. This much times here to here, assume that it is 0.4 milliseconds. 0.4 milliseconds. Okay, so what I can say that this is T1. This is T1 is 0.4 milliseconds. I can write T1 is nothing but 0.4 into 1 millisecond. Correct? 0.4 millisecond I can rewrite like this. That's the reason. 0.4 into what is 1 millisecond? T. T is a period of that waveforms. Okay. So what is this 0.4? Instead of in this case it is 0.4. That's the reason I got 0.4 milliseconds. If this is 0.6, I will get 0.6 milliseconds. Okay. So now, this term 0.4 is instead of writing as 0.4, I can rewrite like, I will assume it is K. This is K. K into T. K into T. Means, what is this K? K maybe, K is 0.4 means my on time becomes 0.4 millisecond. K is 0.6 means 0.6 millisecond. This term K we call as duty cycle. K, what is the K means? Okay, I will tell you. So now, okay, so 0 to T1. There is a one term we have left here, I think T. Okay, so T. So right now I can say that what is yes, R, where is an R comes? R is not there. Okay, I will rewrite. Shall we take? Okay, so if you are having a confused, I can rederive the equations. Average value of the load voltage. Average value of this load voltage from 0 to T1 it is there, no? Yeah, 1 by, so what is the period here? Period is 0 to T. Period is 0 to T. Integration 0 to T1. So what is the value here? What is the value? We are taking average of voltage waveforms. That's the value. What average value is Vs. So this is a T1. Okay, Vs to dt. That is, in denominator T is there. Vs you keep outside. Dt integration T, limit 0 to T1. That is Vs, T becomes T1 0, then T1 by T. What is T1 by T? T1 by T means T1 is on time, correct? On time divided by total time. This is on time, this is total time. So this T1 by T, I am saying that what is T1 by T is nothing but on time divided by total time or period. So this itself we call as duty cycle. In this text, Rashid has used symbol K. Okay. So in some textbooks they will use D also for duty cycle. Any terms you can use. I will use K. Okay. That's the reason this term. Okay, this R is not there here. So T is there here. Correct. T is there. So Vs, same thing. This and this one is same. This one is same. Okay. Instead of T1 by T, Vs into T1 by T, I can write K. Okay, I will continue here onwards. Okay, this is K. So Vs into K is average value. K is duty cycle. So what is the formula for average value? K into Vs. So average value, for an example, if K is 0.4 means on time is 0.4 milliseconds, total time is period is 1 millisecond, means which is an on time? Here to here assume that 0.4 millisecond, here to here assume that 1 milliseconds. So then milli cancel each other, K becomes 0.4. So what is the average value? A is equal to 0.4 into Vs. Vs is how much? As if it is 10, you will get 4. As an average value. See, this is my principle. Means input 10 volt is converted to 4 volts by choosing on time of 0.4 milliseconds and off time of 0.6 milliseconds. Total period, if it is 1 millisecond, if it is 1 milliseconds year to year, if on time is 0.4 milliseconds, off time should be 0.6 millisecond. Okay, this period, whatever we say, this is period, we can switching period. Okay, I will talk more about that. Right now what we learned is average value for the step down DC to DC converter formula is VA is equal to K into Vs, where K is the duty cycle. By changing the duty cycle, we can change the average values of the load voltage. Okay, so this much we learned right now here. Next, so we are one by one we learn average values of the load voltage is K into Vs. We have studied how to derive it, what is duty cycle, everything. Then next, here you can see here we'll calculate RMS value for this voltage. We'll calculate RMS value for this voltage. So just like previous, we are calculating RMS value for this. You say output RMS, in textbooks he has said it as RMS value of output. I am saying like this, textbook he has used a term V out. Okay, I will use this more descriptive term, RMS values of the output. This is equal to root mean. Mean is 1 by, what is the period of oscillation? T. So how my waveforms looks like, can you keep that in mind? This is my on time, this is my on time, this is my on time, so this is my off, this is my off time, so this is my on time, this is here to, then again it repeats, so here to here, what is the timings? T, here to here, what is this timings? Actually it is, if you call this as a 0, this as 0, then this is actually T1. T1 means what? Actually otherwise you can call this as T1, or else this timings I can say KT. KT means duty cycle. T1 is nothing but KT, correct? Because T1 is 0.6 means I can say that 0.6, 0.4, then 0.4 into T is KT. Both you can use the term. So here we have shown it. See, you can call this here to here time duration as T1, or else you can call here to here time duration as KT. TT. This is T2. This is T minus KT. T minus KT means, I will tell you. Okay. KT. This is total time is T. This amplitude is Vs. That's the reason RMS value is root mean square. What is amplitude? Vs. Its square is Vs squared. Okay. Non-zero, 0 to Vs, it is starting from 0. I am integrating till T1. 0 to uh, Vs, this is Vs squared, okay. So root mean square value dt. So this is nothing but root 1 by t. Vs squared you can keep outside, dt you can write t 0 to t1 root call this as Vs squared by t. This t can call as t1, dt integration is t, so 0 to t1 minus 0 t1, okay. This is nothing but Vs I can keep outside, root of t1 by t. What is t1 by t? On time by total time, that is nothing but k. We have already used the term k is nothing but t1 by t. So what is the formula for RMS values of the load voltage? RMS values of the load voltage is Vs into root of k. Vs into root of k, or else sometimes we will write as root of k into Vs. Both are same. Okay, so we studied what is an RMS of the load voltage. Then, so we'll say what is the input power and what is the output power. Okay, so first of all we'll calculate output power. Okay, the output power is, we'll say P naught. Output power we'll say is equal to P naught. P out is equal to, what is that? So integration, again power is product of current and voltage, correct? So we are calculating average output power. Output power is nothing but average value, always it is. Again 0 to t integration, 0 to t1. What is voltage? It is a product of voltage and current. So what is the voltage waveforms? Voltage waveform is having a value Vs from 0 to t1. So current waveform is also having a value Vs by R from 0 to t1. 0 to t1. So that's the reason 0 to t1 only we are having non-zero values. Voltage, instantaneous voltage value will write, and instantaneous output current, because we are calculating the output voltage and output current. So we need to use this IO and we need to use this VO. This is output voltage into dt. So that's the reason this is 1 by t. So what is a V naught? What is an instantaneous values of V naught? So we have seen here, what is V naught? V naught is Vs. What is I naught? Vs by R. So Vs into I naught is Vs by R dt. So this is nothing but Vs and Vs capital letter multiplied each other, Vs squared divided by t, then 0 to t1. So V R also you can keep outside, dt. This is nothing but Vs squared divided by t R into T1, because dt integration is t. If you are having a confuse, you can write t limit 0 to t1. That's the reason Vs squared divided by r 1 by t into, this is t1 minus 0 t1. So t1 by t is nothing but k, that is Vs squared divided by r into k. This is output power. So this is output power. Okay, so next we'll calculate input power. Input, will calculate input power. So I will say that P I, okay, input power Pi. So what is that? Similarly, so then we need to consider this. See, if you plot the input voltage, if you plot input voltage, so you are not plotted right now. I'll plot Vs. So what is the Vs? Vs is Vs, it is lowercase vs. I said it is having value of capital letter Vs. For an example, if it is 10 volt, 10 volts, this is 10 volt for all values of t. Here this is an independent variable t time, it is amplitude or magnitude, so it is Vs or 10 volts for all values of t. But okay, so what is the formula for Pi? Similarly, we are taking for one period integration 0 to we'll see. So it is product of source voltage into source current into dt. Source voltage is existing from 0 to timings. This is t1 or kt. T1, this is timings is how much? T. This is time. Yes, source voltage is existing from here to here. Okay, strictly speaking, I should write here till t, because source voltage is existing. But Is, what is Is? We'll see. See, Is, so we'll check. Vs is existing. What is the Vs value? Vs value for all these times, it is capital letter Vs, or if you take 10, 10. Okay, this is Vs value for all these values from here to here. It is capital letter Vs, capital letter Vs. So it is Vs, capital letter Vs. Then into Is. What is Is? See, this is a current which is flowing here, which is a current which is flowing here. This is, I will say, Is. If you check this circuit, if current is flowing in Is, it should flow in I naught. Correct? Yes. So Is is, when the switch is closed, is same as I naught. And when the switch is open, what is Is value? Is value, what is an Is? See, if you say this is Is, in this source side, this is Is, and in the load side, I will plot this as I naught. Okay. What is Is? Is is 0 when the switch is open. What is Is when the switch is closed? Is is same as I naught. I naught. That's the reason I am having an I for I naught. It is I naught. Okay. I naught picture we are having. So that I can use it for Is or I naught, because both are in series, both are same, both are in same. But thing is here, whether it is Is or I naught is existing only from 0 to T1, from when the switch is closed. So it is 0 value from Kt to T, or from T1 to T, when the switch is open. So what is the final thing what I am saying here? This IS value, this IS 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 like this. IS is Vs by R. It is same as my V naught when the switch is closed, that is timings from when t is existing from when t is greater than 0 or less than or equal to t1, and Is is 0 for when t is greater than t1 or else I can say that when t is greater than t1 and less than or equal to t. This is off time. That's the reason this Is is having non-zero value only during this time and is having zero value during this time. So anyhow we are taking product of Is and Vs. The product also will becomes non-zero only from 0 to t1 and it becomes 0 in between t1 to t. That's the reason. So if I am using anyhow Is formula is Vs by R. This is true only for 0 to t1 and it is 0 from t1 to t. So anyhow when you take a product of these two, the product is also having non-zero value only from 0 to t1. So there is no requirement to take integrate from t1 to t because it is anyhow 0. That's the reason. So Vs into Vs is a product, so it is Vs squared, and in denominator there is a t, so then R I will write here 0 to t1 dt I will write here. Okay, so Vs squared by R into t, so dt is t 0 to t1. So Vs squared by R then 0 to t1. So here t is there, this is t1. So again it is Vs squared by R, t1 by t. What is t1 by t? So Vs squared Vs squared by R into k Vs squared by R into k. Okay, Vs squared by R into k. So this is my Pi, input power. So if you check input power and output power is same. The output power formula also we got Vs squared by R into k, and input power formula also we got Vs squared by R into k. So we got both are same. Why means we have considered that the switch is lossless, means there is no drop in between these two terminals. If you consider this is a transistor, we have assumed that the collector to emitter drop, the current, while current is flowing from collector to emitter, drop occurring in between collector to emitter is 0. And if you are thinking that it is a MOSFET, the drop in between drain, in between drain and source, is 0. In between drain and source is 0. Okay, if this is drain and source, in between drain and source is 0. If you are considering an IGBT, we assumed that the drop between collector emitter is 0. Anyhow, the drop across the switch, when the switch is in on state, we assumed it as 0. The drop in between collector to emitter or in between drain to source, we assumed as 0. We have assumed that this switch is behaving like ideal. There is no voltage drop across this, means there is no power consumption by this switch. Anyhow, so but there is no such switches in the world which consumes 0 power, or else which is having 0 on state drop. Yeah, very small drop is existing in between these two terminal. Means if it is a transistor in between collector and emitter, if it is a power MOSFET in between drain and source, there is a small drop. It may be nearer to 1 volts or in and around 1 volts. Okay. So, but if you consider that drop, for an example, if 10 volt is there, if 1 volt drop is existing here, so what is delivered to load? 9 is delivered. So here ideally we said yes, or else we said if input we assumed as 10, then ideally I will write this as a 10. Actually it is 9. Here then I should write it is 9 by R. Means what I am saying, across this switch, here onwards, this switch I will call as chopper. In all DC to DC converter, instead of switch we say it as chopper. Okay. Across this switch or chopper there is a small drop. That drop we will call as chopper drop, VCH, or a switch drop. It is maybe a small 1 volt or 2 volt. If you consider that, then output power is not same as input power. If you don't consider, means if you neglect the chopper loss, the output power is same as my input power. In all these analysis, whatever we did so far, we have neglected the chopper loss. That's the reasons we got the same formula for output power. We got as a formula output power Vs squared by R into K. For input power we got Vs squared by R into K. So both are same. We got a same formula only because we assumed that chopper loss is 0, means the on state drop of this switch is 0. But it is not actually 0. Only for simplification of my calculations, we are assuming it as 0. This we should keep in mind. Then one more things. So here, so far we have said this is period. Okay. So I said 1 millisecond. 1 millisecond means here onwards I will introduce one more term, switching frequency. Switching frequency means 1 by switching period. So 1 by t. So switching frequency, for an example, if t is 1 millisecond, 1 by 1 millisecond means switching frequency becomes 1 kilohertz. If it is 1 microseconds, 1 by 1 microseconds, then switching frequency becomes 1 megahertz. 1 megahertz. What do you mean by switching frequency? Means how fast we close this switch and we open this switch. Okay. So right now today's MOSFETs or today's MOSFET supports high switching frequency, in the sense in a faster way we can turn on and we can turn off this. So the total period may be in terms of microseconds. Okay, thank you.